And like I said, particle physics was something that until recently was a really cutting edge area of physics. But now with so much work, we're getting to the point where actually we understand lots of things that we didn't understand before. So let's look at the standard model. So we're going to basically break down everything in the universe into some really tiny, really tiny particles. We're going to start building it back up again by considering how we can combine these particles. And then we'll hopefully be at the same position we were at before, but now with a better understanding of sort of what's actually going on. So standard model describes all the particles that make up anything in the universe. So we have 6 quarks. So we have our up, our charm, and our top, and then our down, strange, and bottom. And it's important to know some certain properties. If I remember correctly, I think a lot of these values are in your data booklet, but sort of having a rough idea is always really useful because it may speed things up at some points, but you always get the data booklet in exams. So the 2 most important quantities that you need to know are going to be their charge, which will always be the top number, and then their strangeness. So the charge of this top line is 2/3 for all of them, which is why they're on the top in the same row. And then their strangeness, oh sorry, not the strangeness. The second property that you should know, where's my eraser, is spin. So there we go. Oh, now I need to get rid of the top. So the spin of all quarks is 1/2. Okay, and then the charge of this bottom line is just -1/3, but they still all have 1/2 spins. So, as well as the 6 quarks, we also have 6 leptons. And the word lepton just means light. So these are all light particles. So light as in mass, not as in bright. And we can break these down into, we've got 3 neutrinos and 3 sort of electrons. So we have an electron, a muon, and a tauon. And each of these has its own neutrino. So we've got an electron neutrino, a muon neutrino, and a tauon neutrino. And so, again, spin numbers are all 1/2. Basically, the spin of everything is sort of given a 1/2 value because, I mean, if any of you do chemistry, you'll know that actually we can have plus or minus a 1/2 spin, but you don't need to worry about that for physics. And what's important about the charge of these is all the electrons have -1 charge, all the neutrinos have 0 charge. Okay. Now, finally, just in terms of the particles, each of these has an antiparticle. So we have 12 particles, and we've got 12 antiparticles, which has the same mass, but opposite charge. Opposite charge, and opposite spin. But like I said, the spin doesn't really take too much place in the physics part of the syllabus. Now, as well as the particles, we've also got what we call the bosons. And these are kind of like, these are basically the particle physics method of explaining forces. So we can split the bosons up into 4. So 1, 2, 3, 4. And we've got the gluon, we've got the photon, and then we've got the Z0 boson, and then the W plus or minus. And the last one we have, which is kind of on its own, which hopefully all of you have heard of, is the Higgs boson. And we'll look at the Higgs boson a little more separately. So all you really need to understand for this part of the particle physics subtopic is, as long as you know that there are 12 different particles and 12 different antiparticles, which basically make up all of matter, then that's really a good place to be at before we move on. Okay. Also know that these bosons are particles which are responsible for forces, and we'll look at the different types of forces they're responsible for in a little bit. Okay, so this is matter and these are forces, and then Higgs is kind of associated with mass, so it's the particle that gives everything mass, but again we'll come on to that in a little bit. So what's important about those particles is we define them as fundamental particles. And a fundamental particle is one that cannot be broken down into simpler particles. So a particle that cannot be broken into simpler. I'm going to use the word constituent, which just means that a part of the whole. Okay, so a quark or an electron is as small as we're going to get. Okay, but so if we can't break them down, let's think about how we can build them up. So we have the umbrella term, which means hadron. And this hadron, lepton meant light and hadron means heavy. And we can split those into mesons and baryons. But the key thing is that baryons and mesons are just collections of quarks. Okay. Now, a typical structure of a meson, I would always remember the Me is kind of like a middle or a medium particle. Whenever we make larger particles, a key point is that we require the charge and spin must both be whole numbers. Okay. So for a meson, I can either have I need to have a combination of two particles that are going to add to make a whole number of spin and a whole number of charge. Well, spin, because I've got halves, they're always going to give a whole number if I use 2. So mesons are 2 quarks, but the important thing is we can look a little closer and we can say that one is a quark and one is an anti-quark. So actually I'm going to we'll rechange that to say 2 particles. So a meson is 2 quarks. 2 particles. And it must have 1 quark and 1 antiquark. And then a baryon, well, this one is going to be 3 particles. So it's either going to be 2 quarks and 1 antiquark, actually, no, I don't think that's a possible thing. We'll look at what's going to be possible in a little bit. But it can be 3 quarks, or it could be 3 antiquarks. Yeah, I don't think that. I mean, we'll look into it a little bit when we see how to define the structure of a different baryon. So what I'll do is we'll apply that idea to protons and neutrons, hopefully to make things a bit clearer. So for a proton, I know that a proton must have a +1 charge. And I also know, because I've never heard of strangeness before, it must have 0 strangeness. So if I think back to the fundamental particles which I defined earlier, well, an up quark had +2/3 charge, and it had 0 strangeness. And a down quark had -1/3 charge, and also 0 strangeness. So knowing that a proton is a baryon, which means I need to have 3 particles inside it. Well, if I have 2/3 plus 2/3 minus 1/3, that gives me a +1 charge. So a proton, which I'll call a P+, is actually an up, up, down. So it's 2 up quarks and 1 down quark. And the thing is, if we were to look at the mass of the quarks and the mass of the proton, we'd see that, and also the energy, we'd see that it matched between the two. Now we can do a similar thing, just looking at a neutron as well. So still using just up and down quarks, I now need a 0 charge and 0 strangeness. Well, if I have +2/3, but I subtract 2 lots of 1/3, then I also get the same 0 charge that I wanted. So a neutron is equal to an up and 2 down quarks. So these are 2 that I would definitely remember. But a P, I would almost say this is PUD, P-U-U-D. So a proton is up, up, down, PUD. And then a neutron is up, down, down. So it's a NUD. Okay, so PUDs and NUDs. But this hopefully demonstrates the idea that these quarks, which we know now are the building blocks of everything, if we look at the properties of an overall meson or a baryon, then what we can do is we can work out their quark structure or a possible quark structure using the charge and strangeness values that we know that we need to have.